So welcome everyone. We are back to our second day of DinAmicI, and it's a great pleasure for me to introduce our first speaker of the day, Professor Ledrappier from Paris, correct? He's going to talk for us about the dimension of Furstenberg measures on flag spaces.
Thank you, and thank you for the invitation. It's really a great pleasure to come back here. In fact, part of the story started when I came here for the first time for the inauguration of this building some time ago. And okay, so the general setting is a discrete group of matrices. And if you have a discrete group of matrices, you are interested in a good space on which it acts. And the good spaces, since Furstenberg, we know what they are. If you are matrices, and even in general for semi-simple groups, we know what are the good spaces, the spaces are the most significant for the action. And there are the flag spaces. What is a flag? A flag is an especially partial flag because you have it's complicated. When D is bigger than 2, you have a huge variety of, not huge, you have a variety of objects which are all natural, and a flag is a flag. I mean, it's a succession of subspace, finite dimensional subspace, which are within one another. And of course, the matrix acts naturally on a flag. It's a compact space. It's algebraic. It's very nice. And a little notation. If you want to know the dimension, for instance, of that space, you just have to count how many pairs are separated by the PIs, the size of the dimension of the space. Okay, and the dimension is the number of that number of pairs, and I mean the rotation acts naturally on that space, the compact space. There is a metric which is invariant by rotation, and that's the metric that's the natural metric on the flag space. And for more than technical, but it's easier to think that way, we assume that the group is Zariski dense. So it's not degenerate. It means that SLDR is the right setting for talking about it. If it's not Zariski dense, it means that there is a smaller algebraic group, and you should work in that group. Assuming it's Zariski dense, it's easy way of saying that we are in the right setting. And then it's a fact, it was observed by Yves Benoit, that if you have a Zariski dense subgroup, any partial space of partial flag, there is a unique minimal set for the action of the matrices. So you have a minimal set, you have a group acting on a compact space, and you have a unique minimal set. So we are in good shape for the dynamics. And I mean, we should think of what happens in dimension 2 as a guide. So in dimension 2, what is a group in a SL2? It's a group of, you can think of it as a group of isometries of the hyperbolic space. So then there is only one space of flags, because the space of the projective space in R2. I mean, in R2 there is only one flag space, and the limit set. Maybe I should draw a picture. So you think of your group SL2 as a group of isometries of H2, and you have a discrete group of isometries. And if you look at the orbit of a point, take a point in the middle, and look at the orbit of a point, it's discrete, so it accumulates at the boundary. And the limit set, what's called the limit set, is the set of accumulation points. Okay, no, the boundary is not exactly the flag space because it's the projective space, but it projects on the space of direction into the unique minimal set that I was talking about. And the the space the group which are easier to analyze are the what's called convex co-compact. Convex co-compact, what's maybe the dynamic definition. So you have this limit set, which is a Cantor set. And if you take two distinct points at the boundary, there is a unique geodesic going from here to here. So the product, the set of disjoint points in the boundary, which is lambda cross lambda, lambda gamma cross lambda gamma, the prime mean distinct, multiplied by R, you can think of it as the unit tangent bundle of the hyperbolic space. I mean, a piece of the unit tangent bundle of the hyperbolic space. And what does that mean? That you are in the limit, you end up in the limit set. It means that infinitely often your geodesic is not too far from point of the orbit, which means in the quotient space, your geodesics come back infinitely often. So if you look at the quotient of what is over there, I hate this guy, but if you look at the quotient, asking that it's convex compact is asking that the quotient is compact. And as I said over there, it's asking that the non-wandering set of the geodesic flow is compact. So you think of your manifold as something like that. And convex co-compact means that the non-wandering set of the geodesic flow, the set of geodesic which remains, we don't go to infinity, is a compact set. There is no, it's finite type, and there is no cusp. And then you have one number, you have two numbers, which are natural to describe the size of gamma. One is the Poincaré exponent. And the Poincaré exponent is just the critical value of the series exponential minus the distance. You look at all the distance from 0 to gamma 0. You form that series. And for s equals 0, it's infinity, of course, because gamma is infinity. And for s is very large, it's converges. So there is a critical point. There is a critical value in the middle. And that value is the Poincaré exponent, is also the growth rate, the exponential growth rate of the number of points in a ball of radius r. So that's one number which tells you how the geometry, how gamma is distributed inside, how the orbit are distributed inside. And the other number, which also is of interest, is the dimension of the limit set. So you can think of the Hausdorff dimension, if you are fancy, but even something which is rougher is the Minkowski dimension. Minkowski dimension, you just cover your set by ball of radius epsilon, and you look at the growth rate of that. So that's two numbers, and there is a theorem by Sullivan, and I think he exposed it in 81 here, in this room. And I don't claim that I understood a lot, but and the theorem says that the Hausdorff dimension of the limit set is the same as the Minkowski dimension, is the same as the Poincaré exponent, and it is the topological entropy of the geodesic flow restricted to the non-wandering set, topological entropy of the geodesic flow. So these numbers are the same, and the proof nowadays is very, very classical and something that you will teach about if you make a course on that kind of things. So the first inequality is completely general about dimension. The Hausdorff dimension is always smaller than the Minkowski dimension. And to prove that, to estimate from above the Minkowski dimension, you have to just to find the cover and to count the element of the cover. And how do you cover the limit set? You cover a limit set by shadow. So what is the shadow of a point? It will be all the points at infinity, such that the geodesic doesn't go too far from that point. Or if you so that's a shadow. And I mean it's hyperbolic geometry is not very hard to see that the size of the shadow is an interval, and the shadow is of size e to the minus the distance 0 gamma. So the critical exponent for this series, or the lim sup of log of that number divided by log 1 over epsilon is the same. I mean, it's exercise of first year exercise. Okay, so far it's clear. And why we have equality? We have equality because delta gamma, the Poincaré exponent, is smaller than the Hausdorff dimension. And so we have equality. And why it's smaller than Hausdorff dimension? If you want to estimate from below Hausdorff dimension, there is no secret. You have to find the measure. You have to find a good measure so that the measure of the ball is given roughly by epsilon to the power that you want. And then, because Hausdorff dimension with respect, I will talk next week about that. Hausdorff dimension with respect to Minkowski dimension you cover by balls. Hausdorff dimension you cover by balls of radius smaller than epsilon. So you can be much more clever than just by ball of radius epsilon. And but being more clever, it's so clever that you get completely lost and you cannot control it. But the control is by some, if you have some probability, which always gives you the measure of the ball, and this is a capital B. This is a capital B is the ball of radius epsilon. If you have roughly the good estimate, then the Hausdorff dimension has to be at least delta. So if you put the three inequality together, that gives you the three first inequalities, and the topological entropy. It's because you can the construction of the property of the Patterson-Sullivan measure. For those who know, you recognize also as a measure that Margolis constructed 10 years before, and it gives you the measure of maximal entropy. I mean, that measure is equivalent to the lift of measure of maximal entropy. Okay, so that's very nice. So we have so now the question is, what happens for SLD? And that's what I want to talk about, essentially. So the hero of the preceding story was the Patterson-Sullivan measure. So Patterson-Sullivan measure in higher rank has been constructed by Jean-François Quin, and they have nice property, but not enough to be completely able to do the same thing as Denis. So what we tried, did I say that all this work is joint work with Pablo? So what we tried is to replace Patterson-Sullivan measure, which exists, but we are not able, for instance, to prove this estimate on the ball. If we had this, we will be happy. I mean, with the suitable delta gamma, which I will explain in a moment, we would be happy, but it's not that clear. But we are able to do that for stationary measure for random walks. So I have to introduce some vocabulary. And so we want to construct measure at infinity. So now the same picture, but no, it's not exactly the same picture. So we look on a measure on gamma. We have a group of matrices, and we want to have finite first moment, suppose, and finite entropy. Let's assume it has finite support, for instance. It will be okay for most of what I want to say. And then if you have finite entropy, you can define the limit entropy because the right-hand side is subadditive. And you can define also the Lyapunov exponent because also, again, the right-hand side is subadditive. So you have these two limits, which are given by just by the limit of a subadditive sequence. And there is...
It's easy to define
mu n. Sorry. So you... yeah, you look at the random walk starting with mu, so mu n. Mu n is the n times convolution of n times convolution of so you think of the random walk as a Markov process where you have a sequence xn, and the next step you choose one of the matrix at random with a probability mu, and you compose, and you progress like that. So you have these numbers. We describe more or less how the progression goes to infinity. I mean, I keep that picture because that's the picture to have in mind for things we go to infinity, even if it's much more complicated, but already the picture is expressive. So so a way of going to infinity, you choose at random one point, and then you choose at random another point, you make the product, and so on, and so on, and so on. And it's easy to see that you go to infinity. You go to infinity, you arrive in the limit set in the case of SL2. And since we made the hypothesis of Zariski dense, there is a nice fact, Margulis-Goldschale, which tells you that the exponents are distinct, which makes all what I would say lighter to express. Okay, so I will have two numbers to define, which are a little more complicated because I have more objects. And so one of these objects is the Lyapunov dimension. So I look at all the differences, lambda, so I have the exponent, and from this exponent, I want to define a Lyapunov dimension. And it will depend on, I want to apply this to any partial Frege space, so I have P, which is a partition of 1 to 3D, and I want to associate a number, and that number is defined that way. I look at some function. I order my differences of exponent. I order my differences in increasing order, and then I define a piecewise linear function, Ly of S, by putting the smallest, up to 1, I take the smallest slope, and then the slightly bigger one, 2, 3, 4, and so on. So it's a concave function like that because the slope are increasing. And the Lyapunov dimension is when this function reaches the entropy. So I have two numbers. I just, in the previous slide, I said I have two numbers. I have the entropy, which is a natural number, and the exponent. And from that, you can define here some number, which is called the Lyapunov dimension. And again, I think Jim York introduced that in the same meeting. I just checked. He was in the meeting, and I discussed with him about it at the time, but yeah. Okay, and if you want to do it on a partial flag, you have to replace the entropy by some partial number which comes from the action on the flag. So you have this number. That's a good start, at least one thing. And you have Osseledet's theorem. Osseledet's theorem, again, I show my age. There was a time in the at that time where every talk in dynamics started with the Osseledet's theorem, but nowadays it's at the middle, in the middle of a talk, even by the only guy who is still alive. And so what does say Osseledet's theorem? If you have a product of matrices above, so in that case, above the shift space, the model for the random walk would be the shift space on the product space with a product measure. And then I have a random matrix depending on the stationary, on the ergodic system. So there is a decomposition of RD into kind of eigendirection, the statistical eigendirection, which are the set of vectors which have the right, so lambda I are all the possible, lambda I and minus lambda I are all the possible growth rate and decay of the matrices applied to some vector. And the Osseledet's theorem tells you that there is a decomposition of the space in two subspaces, which is characterized by the fact that the limit is exactly lambda I. And from the definition, you see that the decomposition is measurable. You see that it is in stationary equivariant. If I start as sigma omega, I just change, but I have to go to gamma 0 V to have the same limit, and so on. So it's equivariant, measurable, and it tells you how the vectors behave. Okay, so now I've acted on my flag space. I have these partial flags which come from Osseledet's theorem. If you here, one way, when you work here on the H2, one way of working with the distribution of the limit point is to think of it as an unstable direction. You do the same construction, and the unstable direction gives you some measure. The distribution of the unstable direction gives you some measure on lambda. Here it's the same. You have, if you look at what comes from the partial flags, which comes from the Osseledet's subspaces, you group them, it gives you a flag, a random flag, which is stationary, and stationary means that the measure that you get has the following property. Mu P. So you go G star nu P nu G. Have a random direction. So I act with it by my matrix. My matrix is also random. And I'm asking, and I'm realizing that the distribution is stationary in that sense. Why? Because the distribution, from the definition, it depends only on the path of the unstable direction. So the unstable direction depends only on the path. It is, the distribution is the same as if I shift, but shifting amounts to multiplying by times 0. And times 0 is independent of the path. So if I write this as an equation, it is this equation which tells you that the measure is stationary. Okay, so I will never finish on time, but so why are we happy with the stationary measure? Because with Pablo, we showed that we have this, for stationary measure for the random walk, we have a number. We have a good number. We know that almost everywhere for the measure, but that's enough to deduce something for the Hausdorff dimension. We have a limit. That's what we did last. I mean, it's about to appear, hopefully. And so once you have this, it tells you that for any such stationary measure, the dimension is smaller than the Hausdorff dimension. That's completely general. And the Hausdorff dimension is smaller than even the inf of the Minkowski dimension. So that's given by what we did. And how can you say more? You can say more if you can say something about the analog of convex co-compact. The analog of convex co-compact is also a little complicated, but that's something which established now. I don't know if the audience is many people familiar with it. It's a notion of another representation. So another, it should ring a bell. So what's, so I have to give the definition. So if I have a matrix, I can take the polar decomposition. I can write it as a rotation, diagonal matrix with entries which are non-increasing, and a rotation. So the rotation might change if the sum, anyway you can multiply, if some of the diagonal are equal, then you can turn in that space. But the diagonal is well defined. It's well defined, and they are called the singular values of gamma. And a representation is called K Anosov, if I take K in between 1 and D, is if a singular value K and K plus 1 are separated and uniformly separated in the sense that the ratio is that grows like an exponential of the word length. If it looks, I mean, it comes from Anosov, and why? If you look at the geodetic flow, if you think of the geodetic flow, so the representation gives you some field of operators in a RD bundle over the flow, and saying this condition is that exactly saying that the K and K plus 1 are dominated. So in this room, it should go by itself, but so it's really a dynamical definition. So that's for K, and it's called theta Anosov if you have K, several K, and complete Borel Anosov if it's true for all K. So that's a property which is the right generalization of convex co-compact. Because convex co-compact in a higher rank, it's an exercise to see that only, I mean, it's no picture like this one. Only co-compact subgroup are convex co-compact in a higher rank. Okay, so we have And still I have to define the Poincaré exponent, the analog of the Poincaré exponent. And again, it's a little complicated, and I define a function which looks like this one, which was introduced by Falconer, in fact. And it's not that function, it's more the inverse function. But, okay, you look at a function which is at slope. You look at the differences for each individual matrix, not the exponent now. For each individual matrix, you look at the differences, you order them increasing, and you look at the function, the same function, b1 up to 1, and then you take the slope b2. And when you arrive here at, no, it's an inverse function. And when you arrive at 3, you go you take the slope. So that's the function. And the Falconer dimension is, again, if R is 0, the sum is infinite. If R is very big, the sum is converging. And it's decreasing, it's decreasing. So there is a critical value for which the series converge. Okay, and if you try to think of it, what it means if d equal 2, it's exactly the same as the Poincaré series. Okay? So that's the result that we have. Yeah, half an hour. So we have the partial generalization of Sullivan result, very partial. So what we can prove is that the other dimension of the limit set, we call the limit set was minimal and unique, is smaller than the number I just defined, DMFP. It's not bigger. That number is exactly the supremum over all random walk of the Lyapunov dimension. And the last remark is that this number is smaller than, is at most the dimension of P minus m minus 1. So assume P theta is theta another for some theta. You know, we take the same we take the same flag space and assume that it has m pieces, and we have some gap. And we said in the paper that we were surprised, and one referee said, "Oh, yeah, it's surprising." The other one, of course, and another far smaller. M is the order of P. P is a partition of the number of space in the partial flag. It's d minus 1 if you take everything. But so we have a series of inequalities. So the sup, if you recall what we had anyway, that the sup that we had before, that stationary measure had a dimension, and the dimension was smaller than the upper Minkowski dimension. If you put everything together, we have that the Falconer dimension is at least, or the sup of the Lyapunov dimension is at least that sup. So if you have a good family of random walk for which we have equality in this inequality, if you can prove that the dimension of the other dimension of the dimension of the stationary measure is equal to the Lyapunov dimension, so it's natural. I mean, then you have it's the right generalization of Sullivan's result in higher rank. But it's not clear. It's not clear at all. And Yeah, in fact, that's what put me somehow in dimension. Jim York, in that same meeting, he introduced the Lyapunov dimension for diffeomorphism of compact manifold. And he asked whether, in general, you had the Hausdorff dimension of an attractor is given by the sup of the Lyapunov dimension. And in some sense, that's what motivate us with the life sign to start looking at the dimension of invariant measure. So everything starts here in this room, and at least for me. But this is not clear. This is not easy. It's not an easy problem. So we have some answer in a very simple case in dimension. if you have the in-chain component, for those who know. And there is a very nice preprint of Jailuni, Venupan, and Disheng Shu, in dimension 3, for the projective space, not for the flag space. They are working on it, but they don't have it for the flag space yet. If the support of nu is finite in dimension 3 for the projective space, then it's true. And for people who know, the proof is an extension of the proof for IFS in dimension 2, that you have the good formula for the dimension, which itself is an extension of the proof by Hochmann that Bernoulli convolution have dimension 1 typically. So that's that kind of difficulty. I mean, that's related to that problem. It's a variation. It's an extension. It should go. And I gave that talk, and someone who is specialist of dimension told me, yeah, but this is okay. Hausdorff dimension is hard, but this one should be easy. I don't. I tried. I looked at his paper, and I didn't. I don't know. Maybe it's easier. Okay, so I have a few minutes for saying something about the proof. So I have three inequalities, three arguments to give. 12 minutes, 4 minutes per argument. That should be okay. To the proof. So the first inequality is that the Minkowski dimension is smaller than this strange number which comes from the Falconer dimension. And the idea is about the same as here. And it was done already by Pozzetti, Zambareno, and Winart in some particular cases. And it was done also by Polycott, Simon, in other. I mean, it's something which is when you try to do it and you do it. I mean, it's not. There is no surprise. And what you do, you have to cover. You have your action on the flag space, and you want to cover the minimal set by shadows. But the shadow now, it's much more complicated. The shadow will be the set of endpoints of okay. You have your action on the space, and you have in your group you have loxodromic element because it's hyperbolic, and image at infinity of loxodromic element are dense in lambda p. And each time have an element, a loxodromic element, have so xi gamma, which is gamma plus, which is the point at infinity. I mean the point at infinity. And if you look at all the gammas, all the geodesic, which coincide with gamma up to some time, R, you can call the R shadow of the geodesic this set of geodesic on the closure of that. So now it's very, I mean, it's not a round ball. In 2 dimensions, it was a round ball, even on Hn. I didn't say it, but Sullivan did it for Hn, I mean, any hyperbolic space. But it was still a round ball. But nowadays, it's not a round ball. It's something which are a complicated form. It's an ellipsoid in lambda, in Fp. And if you have an ellipsoid, you want an efficient way of covering by ball, so you cut it by the smallest axe, or maybe not the smallest axe. You cut it by the right axe, depending on what you want, and it gives you some number of balls of radius epsilon. And the proposition is the way of computing this number of balls, which gives you eventually the first inequality. But, I mean, okay, you have to do it, but it's not. Once you understood that, it's not very complicated.
What is the omega?
Var omega, var pi. No, it's just a number. I say that I take the sum of, if I want to cover by ball of radius e to the minus zeta, I look at how, if zeta is smaller or bigger than log si over j, and for all the one for which it's smaller, I don't count them, and for all the one for which it's larger, I count them one. I mean, I count them exactly that number. That's a way of describing this, in numbers, this picture in a more precise way. It's varpi. I like varpi. I mean, okay, so the second inequality is that the Falconer dimension, the one which appeared naturally in the picture, might be obtained as you can find a random walk which approximates as much as you want the Lyapunov dimension. So that the Lyapunov dimension of the stationary measure approximates as much as you want the Falconer dimension. Okay, so it's an equality. So there is one inequality which is it's a variational principle. So it's a variational principle. That's the one you are used to. One inequality is easy. It's just saying that if n is large, you have some number of matrices, which is given by a entropy, for which the singular value are roughly what you want. So if you compute the Falconer sum for each one of them, it gives you something like e to the n h mu plus epsilon times e to the n h mu minus epsilon over 2. I mean, you're careful. It's something which diverges if you are smaller than if you compute Falconer functional a little before the dimension. Well, that's the usual variational principle. Of course, you have to enter into the computation. But and the other relation, which is one we had several wrong proof of it, and there was a proof by Lip and Shu in the same not in the same paper, in a companion paper, because they had to have the help of a student of Shu, which is Jiao, and in the case of Borel and Azoff. And what we did more or less the same proof in the case of, in general case of Azoff. And as one referee told us, it's interesting because there is a paper by Day, a recent preprint, which shows that only hyperbolic, surface group and free group can be Borel and Azoff in SLD. So you have to go beyond to other groups than surface group and free group. Okay, so I just give the idea because I want to. The last slide is a proof. so I want to arrive to the last slide. So the idea is you look at the definition of Falconer dimension. It gives you sets, big sets of matrices, big in the sense that they have roughly e to the size is given by the entropy, and the singular value and the norm, and the singular value are roughly what you want. I mean, something to realize the Falconer dimension. And they have roughly the same norm. You can arrange that. And as mu k, you take the uniform measure on that set. So it has the right entropy, it has the right singular value, but now you make random product. So if you make random product, the entropy decays and the singular value change, and you are completely lost. So you have to take a subgroup, subfamily, which is still good, still has the right number, and still has the right exponent, but such that you are sure that when you compose, you get the good entropy at the end and the good exponent at the end. And how do you do that? There are two tricks. One is, in fact, is a construction inspired by Wang Yang. In a hyperbolic group, you can find sub-semigroups which are free without losing too much. In the free group, if you take a semigroup, I mean, it's not necessary, but if you take all the elements which start with A and finish with A, if you compose it, it's a free semigroup. So if you have a free semigroup, if you compute the entropy, it just is the same. You don't lose anything. And the same for the composition of singular values. It uses Zariski dance again. There is a lemma by Abels, Margolis, Sochert, which tells you that, in fact, you can arrange so that the singular value are... Okay, so it has been used by Breuil, it has been used also by Yves Benoit, but it's more or less, this also is more or less classical for people in the field. 2 minutes. 2 minutes to prove the dimension gap. Where the dimension gap comes from, it's an observation that since the group is hyperbolic, the entropy is realized at the boundary on the group. I'm just a group hyperbolic, I have a boundary, the entropy is realized there. That's something Kajmanovic, or I did also. And now we have this mapping here. Go from the boundary of the group into lambda p, but also into all Grassmannian. And they are still injective there. So these are injective, the entropy is the same. But for each Grassmannian, the entropy is bounded from above by the exponent. I mean, entropy is smaller than exponent. And then, from that relation, the entropy is smaller than that, you can conclude the last thing, and I did the computation in the case of 3. Why? Because it tells you that if you look at the projective space, the entropy is smaller than lambda 1 minus lambda 2 plus lambda 1 minus lambda 3. And that's the projective space in dimension 3. It's the space of direction. If you look at the space of planes now, you get that the entropy is smaller than lambda 2 minus lambda 3 plus lambda 1 minus lambda 3. So if you add the 2, it gives you 2 h mu smaller than 3 times lambda 1 minus lambda 3. And this means that the dimension, that function is smaller than 5/2. Okay. Why? Because if I compute the function at 5, I have T1, the first difference plus the second difference, plus half of the third one. And the sum of the first two is lambda 1 minus lambda 3. half of the third one is lambda 1 minus lambda 3, so I have 3 halves of lambda 1 minus 3. That's bigger than h mu. So definitely the function is 1. I made my proof. That's all. That's finished.